Hello, we continue with the bar optimization problems that we were discussing in the last lecture, where we had considered this problem. Let us just write the problem so that we understand and recall what we had discussed. So, what we were doing was minimize the strain energy of the bar, which is of length L. So, strain energy is given by half E A u prime square dx, and our variable was A of x, subject to we have governing equation, because u is a state variable, E A u prime plus p, the loading is equal to 0, and then we had the volume constraint, that integral A dx minus v star less than or equal to 0. As we had discussed, if you have a functional constraint, which is a second one, we use uppercase Greek letter and put the Lagrange multiplier. If you have a function type or local type constraint, Lagrange multiplier will be a function, okay, lambda x. With that we wrote Lagrangian. So, the way, if you recall, we wrote Lagrangian and we took variation of Lagrangian with respect to area of cross section equal to 0. That gives us what we called design equation, and then when we take variation with respect to the state variable and equated to 0, that gives us what we called adjoint equation or adjoint equilibrium equation. And then we have the governing equation and the volume constraint, and we also have the complementarity condition, that is lambda times, we have the inequality. When you have inequality, we have complementarity condition, say 0 to L A dx minus v star is equal to 0, and we require lambda to be greater than or equal to 0. This is what we call complementarity condition. The reason I am repeating this is that if we understand the bar optimization problem, we can actually do any structural optimization problem. Again, the steps you note from the problem, where we always have to write the data. So, we are given L, Young's modulus, and the loading P of x and V star. Given these, what we need to find are area of cross section. Of course, we need to find these area of cross section and the state variable u of x and lambda x. So, we have 3 functions 1, 2, 3. We have to count whether we have those equations. We have design equation, would say differential equation, adjoint equation, differential equation, and equilibrium equation, differential equation. We have 3 differential equations and 3 functions that are not known. We use the differential equation to solve for u of x, and then we use adjoint equation to solve for lambda x, and then we use design equation to solve for A of x. These are the steps. And then we also have the lambda, uppercase lambda, Lagrange multiplier correspond to the volume constraint. For that, we have this complementarity condition, either lambda is 0 or integral A dx is equal to V star. Okay, either this are 0, that are 0. When this is 0, we say the constraint is not active. When this is 0, that is the portion that we have here, when I say this is 0, then the constraint is active, because volume is constraint is satisfied. Then lambda can be 0, or when it is not 0, it should be greater than 0. Okay. These are the steps. So, we had taken for this problem, after solving, we had taken a special case of P of x equal to P naught, that is uniform load everywhere, that is we are discussing. Let us recall a bar problem. If this is the axis of the bar, we are trying to determine the profile of the bar, whatever that area of cross section, we are trying to define this. So, this is our area of cross section. Okay. This is what we are trying to do, right. And what we had assumed to solve it analytically was that there is a uniform loading P of x. Okay, there is a uniform loading P of x for that, which is we said is P naught. Then we solve the problem analytically. What if we have a function that cannot be integrated, right, or is it tedious to integrate? Then we want to go for a numerical method, which is what we will discuss today, and also see how this problem can be solved in Matlab. Okay. So, what we do is we have the design equation, that is our starting point for the algorithm, design equation, which will be of this form. There will be something, you know what that something is from the previous lecture, plus lambda times something equal to 0. And we had also mentioned that this something will be the gradient of the objective function. In this problem, the objective function is strain energy, objective function. When I say gradient, it with respect to the design variable. In this case, if the objective function what we have here is dou SE by dou A, that is what this will be. Similarly, this will be the constraint, that is the dou volume by dou A. In general, this will be objective function gradient, this will be constraint gradient. This is a gradient of the constraint, functional type constraint that we have, which is volume. That is what we have. In general, this is not strain energy, this will be objective function. Here it is strain energy and normally constraint, but here the constraint is the volume. So, here it is strain energy in this problem and this is volume, that is what we will get. Okay. And from here, by knowing that in this particular problem lambda is equal to u, that is adjoint variable or Lagrange multiplier lambda of x is same as u of x, we got an equation that was design equation, which became simple enough to interpret, saying that strain should be constant everywhere, u prime equal to constant everywhere. Okay. So, basically that how we solved the A of x in this problem. Okay. Again substituting that back into the equilibrium equation. In general, that may not be possible, that is interpreting that u prime equal to constant and using that in the equilibrium equation and solving for A if the function that we are given P of x is not integrable or difficult to do it. In which case what we do is to use iterative scheme where area of cross section, let us say in iteration k plus 1, we would obtain it from area of cross section from k plus we would add this thing, when I say that whole thing, which is the design equation, which should be 0. If we have indeed found an area of cross section that makes this 0, we are done. Even if you go to next iteration k plus 1, your area of cross section kth iteration will be same as area of cross section at k plus 1 iteration. When it is not 0, it will get there, meaning that if you iteratively do it, as k increases, these two will be the same. So, these two will be the same, will be the same if this, by this I mean that thing, if this is 0 and that is what we want here, right. And that is why it makes sense to say that if this method of iterating, we call it actually fixed point method, which we had discussed last time. Also in the case of structural optimization, we call it optimality criteria method, optimality criteria method. It should be used in plural even when there is only optimality criterion. This is the optimality criterion design equation, which we interpreted last time for this stiffest structure problem for given volume as something that says strain is constant. Since we are assuming linear elastic material, stress is also constant, and hence strain energy density is also constant. Okay. That is the optimality criterion, okay. And we are using that to update iteratively and solve for the problem. Okay. Now what I will do is I will switch to Matlab. So I hope those who are taking the class know how to use Matlab. These codes are available to you. You can also run it offline, but I am going to just show how this works. Okay. So this is how Matlab looks. There are data files here in data.pdf. You want to see what data we are using, but I am going to show in the code itself what it will be. The main file here is, this is the Matlab file called baropt.m. There are 3 other m files, fembar.m and matcut.m. So I will highlight, this is bar.m. You have to look at the, open the file and see it. In the screen you may not be able to see it, but let us say that there are fembar, matcut.m, veccut.m that you do not need to touch. Okay. Baropt.m is what you can run and also change. Okay. Let us look at this problem. Let me first just run it and show what we get. Okay. When I run it, it is working on. It gave us a result like this. Okay. Here x, let me make it a little bigger, x here goes from 0 to 10. That means that we have taken a bar of 10 units long, you can call it meters if you will, and on this side we are showing the area of cross section, the y axis, or sorry, we are showing the breadth of the rectangular, square, whatever cross section. The breadth is being shown on the y axis here. For this problem, the optimal cross section profile looks like this. This break that you see is basically, there should be a lines here. Okay. So joining here and here, there is a jump. Okay. There will be a reason as to why that jump is occurring in the data that we have given. So let us now go back to the code and then see what we are doing. But you will have the code available to you on the website, so you can take it. This was written by one of my students, Gaurav Nair, in 2011. All students who take this class write their own codes. I am sure you also will be able to do it. It just is given to you so that you can see how it works. There are some basic housekeeping commands, as we call them, clearing the figures, clearing all variables, and clearing the screen, and hold off on the figure so that if you draw something new, previous one will not be there when you do it. The data for this problem, we are taking length of the bar to be 10 units, okay, that is 10 units, and we are discretizing the bar to 200. Let us remember that whenever we do structure optimization in a computer, we do not do analytical, we do it discretized way. That is, we have broken the bar into 200 parts and trying to make the area of cross section of each of these barlets or bar elements to be different from one another. That is what we are doing. Even though a continuous function a of x we got, when you do it in the computer, you discretize and do it. That refers to number of discretizations, and V star is our volume that we are taking 20 units here, and the D, which is the diameter if you take circular cross section, that is a rectangular cross section here, the depth is taken, that is fixed, not diameter here, depth of the cross section is fixed. As you saw, the breadth was the variable. So, area of cross section we are defining initial approximate area all ones, okay, times 6, right, that is being taken. N is the number of elements, we are just taking 6, and then the length of each element being computed, elastic modulus is taken. You can change these values as you wish, and then defining several things. We also have upper and lower bounds for the area of cross section of the bar, which we did not discuss, but we will be doing it later. So, we have upper and lower bounds, and then some tolerance for making the algorithm stop when a certain condition is satisfied. And you have to go through the code yourself to see how this reflects what we have derived. Okay. I will point to the critical place where our fixed point method is in action. So, we are specifying the forces, in this case force at 51, that is we have the 50 is the node number, there we are specifying 1000, but I can change, we just ran it. So, what I will do is I will change, I will comment it out, okay, I will comment out this line over here. Okay, that is commented now. In Matlab, when you put a percentage sign, that is line. Now, what we have is uniform distributed force is there, okay, everywhere 20 units. Now, let us run this. All right. So, this is bar opt run and time, that is the one, run code and measure execution time. Okay. This is asking for something more. Okay. Let us see, I will just run this code. Does it run like this? Or we can just type the bar opt here at the command prompt. So, it should be running now. We have changed the loading. Now, if we go to the figure file, right. So, if you remember how it was earlier to now, because we changed the conditions here, that is the force is uniform now. What was there now is not the optimal solution, we had different one. This is the A minimum that we have, and then it just tapers up like this. What are the boundary conditions? Where is it fixed? Let us check that. Okay. So, let us go and check. What we are fixing here is disp id n plus 1. We have n, right side is what is being fixed to a value 0 here. Okay. That is why when we go here, this one, it is fixed on this side and it is free on this side. It is a free fixed case of a bar, and that is why we got a solution that looks like this. Now, what I will do is I will switch, that is I will fix the left end and free the right end. For that I need to go here and make this 1, that is the first node is what you will fix to 0 value, then the right one will be free, right. So, here let us run this. When this command prompt appears in the command window, then that, yeah, it is done now, right. So, if we go back and look at the figure, right, you see when I fix it here and free it here, it comes like this. If you remember analytically, that is what we had observed. When I give uniform distributed load, we get a linearly tapering down profile for the area of cross section. Large area here goes down. It could have gone to 0, that was our condition, but now we put a minimum here, that is why it getting there. To show you that it works, let me make that a minimum actually 0. Okay. Let us go up here, there is a min which is now 0.5, let us make it actually 0. Okay. If I run it now, it is running, command prompt has to come back here to indicate that the program has finished running, which it has now. So, let us look at this. So, at 10 it has indeed gone to 0 cross section. This is what we had solved analytically, but now we have a numerical one. When you have a numerical program, we can put any boundary condition and any loading. We can put the loading whichever way we want. So, what I will do is here the force which I had commented, let me remove that thing and no load there. Okay. Here I will put the load at the last point, the rightmost point. We have fixed the left one, I made it n plus 1, meaning that is the n plus 1 node, the last one, extreme right node, that is where I am applying 1000, and everywhere else I have 0, okay, force. Let us see what solution comes up here. Again it is running, it finished, we got a solution like this. So, here it is uniform cross section. That actually makes sense. If you want to make a stiffest structure for a fixed free bar with a constant load with a point load at the right end, the best solution is simply uniform cross section. That is what we got with the volume that we have. Now, the volume is 2 times the length times the depth that we have specified for the cross section. Okay. So, that way once we have this, we can play with, instead of applying there, total we had 200 elements. Okay. Let us say I apply somewhere as we had here 50th node. Okay. If I run it, so it is giving some errors because something went in Matlab. NaN is not a number. Okay. What we have given 50th node here for the what we are giving. Let us see what the figure also it is not giving, because it actually says that somewhere matrix is singular. So, you have to check why that matrix is becoming singular, meaning its determinant is 0. So, the loading that I am giving at the 50th node somehow is causing the matrix to become singular in the program somewhere. Okay. So, let me change it back to what we had, which is n plus 1. That means, whenever this program does not run or gives an error, you can look at it, but know that something is wrong with the input given. Okay. When input is proper, we got back the solution. Okay. So, let me comment that is I do not want to give an end load, and we can make it again the constant load. We have played with the if I look at the displacement boundary condition, okay, which is over here, we fixed node 1. Let me also fix the last one, n plus 1. That means that the displacement value I have to give another 0. Now, it becomes fixed bar, and let us see what we get. Okay, it is running, as you can see command window, it is done now. So, we got something like this. Okay. But in fact, fixed bar should be slightly different from it. Let me see if I have done it right. 1 and n plus 1, and then 0 0, we have the loading. I have to see f value 20, all of this. Okay, fixed condition, displacement 1 and n plus 1 node. Okay, we can actually see these values, disp id, if that is a variable. Okay, 1 and 201, so that is correct. Disp value is also 0 0, so that part is fine. Iterations are set to 50, the force we have is 20. So, it is giving, it is running something, but result will analyze it later. Let me point out the code now. So, if you see, the loop starts here, 1 to its is number of iterations. Initially the lambda that we have, that is the volume constraint multiplier, initialized to 0. Here is where we are calling the finite element bar finite element routine, okay, and then u dash that returns the displacement state. Basically, this FEM bar routine solves the equilibrium equation and returns u and few others reactions and internal forces and stiffness matrix, strain energy and all that, we are getting u, and then we are computing u prime here using finite difference method, and then here is where we are updating lambda that we have. See, the lambda has to be computed using the volume constraint, and that is being done over here. Okay. So, the lambda one is being computed there, that is Lagrange multiplier. After we have that, the lambda which is computed there using volume here, we are updating the area of cross section. Okay. AE at jth iteration for all the element j equal to 1 to n, we are using the current j and multiplying something raised to some eta. So, if I go back and show our algorithm, if you see here, we are adding what should be 0. Instead, we could also do the following. So, we have the design equation something plus lambda times something equal to 0. Let us call this as let us call this some a and b. So, what I have is a plus lambda b is equal to 0. I can write this as a by minus lambda b equal to 1. Basically, I have taken lambda b to the other side and got it downstairs. So, I have this. If I have this, I can do my area of cross section. Anyway, this A is not area of cross section, I just used A. Now, if I write my area of cross section at kth iteration, if I want, instead of adding something that should be made 0, I can multiply by something that should eventually become 0, that is this A by minus lambda b. Again, this A you may get confused. So, let me actually put some A hat or something. So, that A is not same as this A hat that we have here, okay. Or better yet, let me just so that there is no confusion at all, let us just call it some C. Let us just calling that C, C and C, okay. We are multiplying with what should become 1. This is another way of doing it, and that is what we are doing in this case here. So, we are multiplying that raised to some eta to make it faster, right, and then we are updating the areas of cross section here, and then if anything has exceeded A max, we are setting at A max. If anything goes below A min, we are setting at A min and running the algorithm, and in that process we have to do this as long as this flag that we have, that is A is not going above the upper bound or below the lower bound, and trying to adjust it and get here. Okay. This is just a starting program that you should run, understand each line, compare with the algorithm we have discussed, and learn how to write structural optimization routines on your own once you have finite element routine for that. Here we have FEM bar, which is the finite element routine for analyzing bars, that is to solve the governing equation of the bars. Then you can write this code, then you have structural optimization for a bar. Okay. So, study this code, and we will be coming back to this type of code in the case of beams and other structures as well. We will stop here and continue the next half.